Good morning. Some of us already know Guillermo since a long time ago, but others I think you don't know, and because of that I'm going to make a brief summary of his curriculum. So Guillermo, as you know, he's an invited within the Severo Ochoa framework here. He will be at the ISC until April. And he did the PhD in Manchester. He's Mexican. He has been working in Europe for a number of years, a large number of years. He has been working at ISO, at the Max Planck, at the Instituto de Astrofísica in Paris. He has been invited in the Colegio de Francia also in Paris. And he has been working here at the ISC for a number of years. In fact, he led one of the first international time collaboration. The name was JEFE, and there he put together a large number of people working on the physics of star formation of massive systems. This is the topic of his career. He's an expert in hydrodynamic, of ionized regions, of massive starbursts, and these issues. In fact, he was the organizer of the third winter school. The name was the Star Formation in Stellar Systems. Just as, he has been working in this field, as I said, for a number of years now. He's one of the references in the physics of the interstellar medium. And in particular, maybe you have studied, when you studied the physics of ionized regions, you have heard about the phase that is called the Champagne model, the Champagne flow. This was something that was somehow invented, or not somehow, it was invented by Guillermo soon after his PhD. So some of the studies he has done are now references in the books, even if now they are known by their name without mentioning the origin that was Guillermo. So he's real una autoridad in the camp. So today he's going to tell us about the paper he has just been recently accepted, and deal with one of the different things that he's working on. And this is done in particular with his colleagues in Mexico. He works at the INAOE, Instituto Nacional de Óptica, Astrofísica y Electrónica in Puebla. He there lead a very important group, and he's our contact in Mexico within the collaboration Estallido. So he will be here, as I said, until April, and I will suggest you, students, to take the most of his stay here, because I'm sure he will have many things to share with you. And for sure, he will be very happy to answer whoever you want to visit him and to discuss whatever topic related to the hydrodynamic of the interstellar medium. So he's in the Severo Ochoa room near the GTC meeting room. So Guillermo, whenever you want. Thank you for being here. Thank you.
For having such a good memory and reminding me of all these years. I just want to say something about the Champagne model that gave me a reputation of an alcoholic in the astrophysical group of very high standards, but still an alcoholic. Huh? Yes, I'm going to tell you about the origin, what we believe is the origin of the absorption and emission line components in the spectra of a dwarf galaxy, PHL 293b. All of this was generated by a talk that I attended last year, given by Roberto Televich, who is a very close friend of mine, and he made a beautiful description of the spectra taken by the X-shooter at the VLT. Part of it I'm showing in this transparency, as well as the name of all the collaborators in this adventure. But let me see if I can show everything. You know, this on the upper left-hand corner is PHL 293b. It's a really minute galaxy. You can have some. It's PHL because was found in the Palomar Sky Survey by Faro and Luton in 1962. It's a low luminosity and very compact galaxy at a distance of 23.1 megaparsecs and has a dimension of only 400 parsecs in radius. So it's really small. It's a real dwarf galaxy. Okay? It hosts an a superstar cluster. The cluster has some properties that I indicate here. Apparently, the age is in between 5 and 7 million years and has a mass of the order of 10 to the 5 solar masses. That implies that the number of photons is actually that number, 2.71 times 10 to the 51 photons per second. In its ionized mass has a very similar mass, also around 10 to the 5 solar masses. And it has some very peculiar characteristics on its spectra. Let me see if I can do this. Oh, yes. So, for example, if you go and look at H alpha, in H alpha, you see that there is a very narrow component centered at the velocity of the galaxy. It's totally out of scale. It actually should reach the ceiling and probably the next floor. You know, the emission is really fantastic in the very narrow part. But then it has this amazingly broad emission line here. And the most spectacular thing is that here, right where I'm pointing at now, there's an absorption feature, okay? This absorption feature is shifted from H alpha some 800 kilometers per second. The same thing happens when you go to all the Barnum lines. So if you go to H beta, for example, here, maybe you can see the absorption even better there. Again, the very narrow line that comes from the H2 region surrounding the cluster, then these broad components with much lower intensity, and then the incredible absorption lines that you have there. You know? The spectra, the spectra of the BLT extruder, I showed you completely. This is the other part. Here the wavelength is in microns, goes up to 2.3 microns. So it's absolutely spectacular to have all the lines, all the information you want with one single go, you know, is the extruder at the BLT. So it doesn't reach Lyman alpha, but almost, you know, it's around 3,000 angstroms. And then it goes to 1 micron in this page, and then you need several pages to display all the spectra. It's absolutely beautiful. And the first people who described it were Instituto in 2011, Tenorio-Tagle in 2011, who decided that this kind of spectra, you know, the broad lines and the absorption line had to be caused by a luminous blue variable star, a massive star that is almost on the verge of exploding supernova, and a few years before that, it goes a bit crazy. We don't understand how or why, but becomes all of a sudden very luminous in spaces of 1 year, enormous variations in the continuum and in the lines that we can observe in these stars. And then there was Roberto and his group who actually also looked at from the archive, they also looked at the BLT extruder spectra of this galaxy. And so, for example, Instituto said, well, okay, here's my conclusion. I think this is evidence for a luminous blue variable. This is the narrow line from the galaxy. This sort of thing, the broad line, is going to be a component, really broad, just like that. And then, as I was pointing at you, there has to be an absorption feature, blue-shifted absorption feature. And when Roberto and collaborators last year, they printed this last year, they say that there are two broad lines, this component C and component D. And this is due to the fact that the spectra has a wing, an incredible red-shifted wing on this side. And so here you have the different interpretations. Roberto says that, Roberto and his group said, they say that there is no way that this is a luminous blue variable. And I'm going to show you the evidence for that. And instead, he says it has to be a supershell. It has to be a supershell that is sitting in front of the star cluster. And I'm going to show you that that's also impossible. You cannot have any of these two models are totally wrong. So first I'm going to go into the arguments made by Tenorio-Tagle et al. 2014, saying that it's not a luminous blue variable. So for that I'm going to show you first the evidence from a luminous blue variable. So as I said before, there are strong changes in the continuum over a number of years, from 97 to 2004, here, for example, different lines. And you see that in this visible part of the spectra, not only the lines change, but also the continuum changes a lot. And then if you go in detail to the emission lines, over a number of years, here, for example, from 97, which is this blue line here, you can see that this blue line has the absorption here, and it's a broad line, but all of it is broad. And then from a couple of years later, it changes drastically its intensity, this line, and then it goes on, then it's reduced with the red dots, and then you can see something that is important, is that afterwards, from these 2001, 2003, and 2004, actually the absorption feature disappears. There's no absorption feature. So it's something that is happening in this star, in the atmosphere of this star. It grows in dimension. This is a thing that we don't understand very well. Only observationally we know the details of these luminous blue variables. But the changes occur very rapidly, very quickly. Okay? And then both in the continuum and in the line. And as I said, sometimes the absorption feature disappears altogether. So the properties that we have derived from the 35 luminous blue variables that we can see in our galaxy, and a few more that we have found in other galaxies, we know that they have an actual average speed. They produce an ejection with an average speed of 300 kilometers per second, although Eta Carina, who is also a luminous blue variable, has reached up to 500 kilometers per second. The absorptions that I was pointing at in PHL 293b are shifted 800 kilometers per second. So this is a little bit more than what one would expect for a luminous blue variable. The total mechanical energy of this ejection system is 46 Hertz, and as I said, large variations in the ultraviolet, and also the iron 2 lines with a lambda listed there, sometimes appear in emission, and sometimes they disappear. So, for example, iron 2 sometimes is in emission at 5,000 angstroms or there. And when they disappear, you have these iron 3 lines, sometimes in emission, but then sometimes in absorption, depending on the year that you look at your luminous blue variable. And the mechanism responsible for all these ejections is totally unknown. It's a matter of several PhD students, and this is the case of a dwarf galaxy 2363, a paper by Petit et al. In 2003. So what really Roberto did is, well, let's see if there is any variation in the luminosity of PHL 293b, and for that he went to different archives, to his own data. He looked in all the drawers in his desk, got it out, and here you have the answer. What he calls in the paper about the variability of this galaxy, or the lack of it. Plotted here are the B magnitude for the galaxy over a number of years. Here I have from 2001 to 2015. Particularly the crosses come from the Catalina Sky Survey. This is done in Arizona. and it's something like, let me see, 353 observations of the galaxy over 91 observing nights. So every night they observe this galaxy, every observing night 91 times. They observe the galaxy 4 times, all together in one night, 1 hour. 1 hour they sat on the source, and that's what is plotted with crosses here, crosses. And then the yearly average is here in these diamonds, that you can see over the years. This is the magnitude you derive from this law, and here they are pointing all the excursions with the spectrographs. This is the X-shooter, this is the ICES at the William Herschel telescope here in La Palma. And so the incredible thing, which I have here in blue, is that the average magnitude is 17.056 plus minus nothing, okay? And which means the galaxy does not have a luminous blue variable. And this includes also data from Luz Marina Kairos, from Kinman at the Lick Observatory in California, and implies that there is no variability. The changes are at the level of few tenths of magnitude over the last 25 years. And this is demolishing. Implies there is no luminous blue variable. And then as every time you write a paper with a spectra, you have to give an interpretation. Roberto and his group, they went to say it was something else. But let me show you first something that they derived. Roberto and his group derived from the spectrum. And that is the fact that they were able to measure the column densities of ionized and of neutral matter of the gas causing the absorption feature. So if you want to relate an absorption line, the equivalent width of an absorption line, and the column density of the gas, you have to use a relation like this one that is here. So the column density, centimeters minus 2, has to be equal to the logarithm of the equivalent width at that lambda, divided by lambda, minus the log of lambda times the oscillator strength, F in this equation, plus that constant. And so from the spectra of X-shooter, they have measured, Roberto actually in front of me measured these 0.91 angstroms, 0.68 angstroms for the iron 2 at these wavelengths, from the iron 2 absorption features. If you can simply go to several papers and it's a constant, is this number given here. This is the probability that there is an absorption, the oscillator strength is called. And so from that you can derive the column density of ionized iron, and the numbers come out to be these two, for these two particular frequencies, these two particular wavelengths. And then you have to assume, okay, if the amount of, if the metallicity of my galaxy is about solar, then I will know that the column density of neutral hydrogen is going to be about 10 to the minus 20 centimeters minus 2. If it's half solar, it's going to be a little larger, 2 times 10 to the 20 centimeters minus 2. Using exactly the same procedure, you go to H alpha absorption line, H alpha and H beta, and they measure 6 angstroms and 2 angstroms for this equivalent width, and they derive the column density of neutral material, which you can see here is a number times 10 to the 13 centimeters minus 2. And if you compare the two, if you compare the ionized gas column density, ionized hydrogen column density, to the neutral hydrogen column density, there's 7 orders of magnitude difference, which implies that the gas that is causing the absorptions is incredibly ionized. It's very highly ionized. Okay? Then, as I said, the interpretation that is an expanding supershell with a velocity of 800 kilometers causing the absorption in the spectra of the galaxy is definitely wrong. And it is wrong for several reasons, but mainly because the cluster has survived for about 5 million years. 5 million years. And if you travel with a velocity of 800 kilometers per second for 5 million years, the supershell should be at about 4 kiloparsecs. So it will be miles out of the little galaxy that we are talking about. Okay? Remember, the radius is only 400 parsecs. And so a supershell has a dynamical time that is impossible that it belongs to the galaxy. Okay? So we need something else. Therefore, we need something else. Something else, and I'm going to profit from the fact that I was giving a talk here last year, and so I mentioned several issues, which I think I'm just going to rephrase rapidly. If there are questions, please don't hesitate. I'm going to talk about the matter that is reinserted by stellar winds and supernova inside the cluster. So the superstar cluster that has a radius of about 2 parsecs is a little thing sitting in the middle of this galaxy. And inside you have 10 to the 5 solar masses in stars, and therefore many of them are massive stars, if you assume any IMF, almost any IMF. And the massive stars are going to undergo winds, very strong winds, and eventually, after 3 million years, if they form the same afternoon, all of them, they are going to explode like supernova. And what happens is that they are so close together to each other that the winds from one star will collide with the winds of the neighbor, and the supernova with the winds of all the stars that are inside there. This process is called the thermalization of the kinetic energy injected by the massive stars in the cluster. And so if you have all these collisions of all this kinetic energy, that produces strong shock waves. The kinetic energy is transformed into thermal energy inside the cluster, inside this little box, and that gives an incredibly high pressure inside the cluster. The high pressure, as nothing is happening outside, produces a wind. A wind. This hot gas comes out of the wind with large speed. And then it begins to interact with the interstellar medium that is sitting outside. Okay? In the adiabatic calculations, well, you can actually, you need to know 3 parameters, which are the luminosity of the cluster, the mass deposition rate inside the cluster, and the radius to derive all the hydrodynamics that is happening. Or you can derive the velocity, the density, the run of temperature, the run of pressure of the gas that has been injected and is moving away from the cluster. And if you know these 3 numbers, luminosity, mass, m dot, luminosity, m dot, and radius, then you can easily produce plots like this. You can do this analytically or numerically. It's the same, you obtain the same result. In this particular case, I'm talking about a cluster that has 10 parsec radius, and with that you can see that these are the 10 parsecs. You are depositing matter there inside, and the flow very quickly becomes stationary. Stationary means that whatever you put in, m dot, inside the cluster is exactly identical to whatever is leaving the cluster. Okay? It's stationary. If you prefer an easier, perhaps, example is like when you contemplate a river. You know, as long as in the source you have depositing the same amount of water, you will always see the same river. Not the same water, but the same river. Okay? the same river flowing, passing by, the same density, the same altitude, the same everything. It's stationary, okay? In this case, you produce a stationary cluster wind. So it will always look like that. The density profile will always be the same. The density is larger inside the cluster, and as the wind expands, then the density drops as r to the minus 2. Beautiful also is the temperature here is almost a constant, about 10 to the 7 Kelvin inside the cluster. And as the gas streams out, then it cools down as the distance to the power minus 4th Earth. Very special and peculiar is the velocity. The velocity plot that you have to understand that to produce this stationary flow, you need to have the 0 kilometer per second right at the center. The velocity increases to the sound speed exactly at the cluster boundary, 10 parsecs in this case. And then through pressure gradients, it expands and reaches what is called in the literature the V infinity, the terminal speed of the wind, which is about 2 times the velocity that you had at the surface of the wind, okay? And so this is beautiful and stationary, and if you know one, you say, I know them all. But there's something else. There's another small detail that I want to add to this, because the original model by Chevalier and Clegg was an adiabatic model, and there's nothing that is adiabatic in this universe, okay? So for that, you have to insert into your energy equation a term Q, capital Q, like this one, that considers lambda n squared. Lambda is the cooling rate. The cooling rate is given in this plot. This is lambda as a function of the logarithm of temperature, and this lambda for a gas that is in collisional ionization equilibrium. All the transitions, all the radiative transitions from a gas at a given temperature have been added and are in this black line that you have here. This, for example, accounts for all the recombinations of hydrogen, helium, oxygen 6 to oxygen 5, all the excitations. This part at high temperatures is just the Bremsstrahlung cooling. And then in color you have the cooling that is given to the gas if you have dust mixed with your gas. And look how surprising and beautiful. This is orders of magnitude at high temperatures. Is at least 2 orders of magnitude higher than what you get from the gas. So the dust is receiving impacts from electrons, many of them. You have a dust grain, and the electrons come and hit it, and the solid grain begins to radiate almost immediately in the infrared. Okay? But it takes away all the velocity of the electrons that are right there, crashes with the grain, you remove all that energy from your gas, and you radiate it, the dust radiates it in the infrared. So it's very important, because then we have noticed that if in this diagram that contains the luminosity of the cluster, or if you prefer, the mass of the cluster, as a function of the radius of the cluster. So let's consider clusters of 3 parsecs in size, for example, and you will see that if you are at a given mass, if your cluster has a given mass, a given luminosity, then you reproduce the adiabatic results. The temperature drops as r to minus 4/3. But if you consider more massive clusters and more, then you will see how cooling comes into business. Because if you have a larger cluster, you are putting more energy, but also more mass. And the cooling goes as the square of the density. And therefore, there's a moment when the wind, the cluster wind, begins to cool rapidly, very close to the surface of the cluster. So instead of having a bubble which is emitting only in X-rays, you are going to see that it's actually going to be able to recombine. And so we know this since a few years ago, and now that PHL 293b appeared, we decided to try to make some models for this galaxy. And for that, we use the input parameters that we have derived from the observations, like the mechanical luminosity is between 1 and 2 times 10 to the 40 error per second. The terminal speed, we assumed was going to be 1,000. The cluster radius, we have measured that, is around 2 parsecs, the ionizing photon flux. And we are using those grains, very low amount of those grains. The dose to gas mass ratio is 10 to the minus 3. Well, these are the results of the hydrodynamical models. And show you again curves of velocity, temperature, and density. And the velocity, we did lots of models, but we selected as favorites those that have a velocity, a terminal velocity, around 800 kilometers per second. So these three dotted lines or dashed lines, we decided, well, these are around 800, so we are going to select these three. This model without dust produces the solid line there, okay? If you don't put dust, then you reproduce the solid line. But these three are beautiful because they reach these 800 kilometers per second. So we decided, okay, these are our favorite ones. Then, as I said, in temperature, well, the one that Harley cools, well, this temperature drops as R to the minus 4/3, but the others undergo a rapid transition from a few times 10 to the 5 to they rapidly drop to 10 to the 4 Kelvin because of the cooling, okay? The wind, as it flies away from the cluster, undergoes strong radiative cooling. Density, just look at the density, it's doing its job, it's not constant inside the 2 parsec cluster, but it has the highest densities there. And then it expands, and the density drops as R to the minus 2. So we decided, okay, if you have the gas very hot, just notice here, the temperatures in the center are several times 10 to the 7 Kelvin, or about that value. If you are so hot, the electrons are moving so fast that they don't see the ions. So there is no recombination. But as soon as you reach the temperature of 10 to the 5, the ions begin to see the electrons and recombine. Okay? And lower temperatures even better, because the electrons are going slower and slower. So we have also solved 2 other equations with the values that we know from the hydrodynamics I just showed you, and we solved the equations of the transport of ionizing radiation, and then the ionization balance equation. And so we decided we know the number of photons in the cluster. We know that ionizing photons in the cluster. We know that none of these photons are taken by the hot gas until the temperature has dropped to 10 to the 5. So over there, then we begin to apply this recombination possibility. And we are taking ionizing photons then when the temperature is 10 to the 5. And we continue to do so as we move far away and further away from the cluster. And so this is what happens. What happens is that at certain distance, the radius here, from the cluster, the temperature becomes 10 to the 5 for the models I have shown you. And suddenly, here is the total number of photons that are trapped, that are taken by the recombination. And so it's a number that is growing because there are more and more recombinations in the cluster wind. And then apparently this depletion of ultraviolet photons stops. And this is shown here by the horizontal lines. These lines become almost horizontal. There are fewer and fewer recombinations as you move away from the cluster. And what's the reason? Well, the reason is that the density is dropping. The density is dropping. So you have less recombinations because I'm going back to transparency. Sorry. Here, please notice that here the densities are large. When you reach the distance where the temperature is 10 to the 5, well, they are about a few atoms per cubic centimeter. And further on, very soon, you cross the value when the density is 1 atom per cubic centimeter. And here they are less than 1. And the recombination goes as 1 over the recombination coefficient times n. And so, as you move away from the cluster, there are less recombinations. If the atom is recombined, it doesn't recombine, then it's transparent to the ultraviolet photon. And that's why you don't take anymore when you are at large distances. Okay? But now, oh, this is beautiful. And we know that we produce, because we have lots of photons, we almost take the degree of ionization to 1, but not quite. There are always some neutrons. Notice that there have been some 10 to the 46, 10 to the 47 recombinations. And that's why I have knocked down from the ionizing cluster that quantity of ultraviolet photons. Okay? So if we measure the amount of ionized gas that has been produced by all this after the temperature becomes less than 10 to the 5. Well, we obtained some number 6.6 times 10 to the 19 is between that and 9.5 times 10 to the 19 centimeters minus 2, which I have to compare with the value derived from the X-shooter observation. I hold it was this absolutely excellent agreement. You know, we were not exactly on the number, but it's very close. And similar thing happens for the neutral Coulomb density. So the gas is almost fully ionized, but there's a little bit which is neutral. And that we have measured, and we come with a number which is between 1.5 and 4.5 times 10 to the 14, which is in beautiful agreement with what we derive from the X-shooter. So we know in this region where the cluster-wing gas begins to recombine, is almost fully ionized, but not exactly, not totally. And the question is, where is the absorption coming from? Now, this I want you to take home with you, because this is the key to the spectra of the galaxy. So just imagine you are in your cluster, and this is your spectra that you will see. You will see your continuum, and then if the star has an atmosphere, then you are going to see this gigantic absorption in H alpha, for example, H beta, and in all the higher land. Now, the absorption we are seeing is blue shifted by 800 kilometers per second. And so, if there is a photon from the continuum of the source, from the continuum of the cluster, that is also shifted 800 kilometers per second, when it encounters an atom that is hitting at the level 2 of energy, then it's going to be taken as an H alpha photon. Okay? So, if you go to H alpha, for example, here, and then you move to the left 800 kilometers per second, which is more or less where I put the arrow, then that photon from the continuum is going to believe, when it sees the atom at level 2, it's going to absorb that photon. Okay? That photon will go to level 3. Okay? That atom will jump to level 3. Okay? And then probably, because there are 10 to the 46 recombinations, more ultraviolet photons will ionize it. But there is so much neutral gas. We have used 10 to the 46 ultraviolet photons to sustain the ionization. And so the same thing happens to photons in the continuum around H beta. If you move 800 kilometers per second, and that means if in your expanding region that has recombine, that is moving, the water in the river is moving with 800 kilometers per second, then you are going to take this photon from the continuum and you are going to make your absorption. Okay? That's how you make absorptions into your spectra. So don't forget this whenever you're going. You are taking photons from the continuum, not ultraviolet photons. You are taking photons from the continuum. So we understand then the absorption feature. Now let's see if we can understand the broad lines. The broad lines, components C and D in this interpretation. Well, we believe to have such speeds, you need a very energetic event, supernova. Okay? Now, these are tricky supernovas because the two broad lines are redshifted. Redshifted, one by 50 kilometers per second, the other one by 2,000 kilometers per second. Okay? So if you look at the galaxy and you see these gigantic expansions redshifted by so much, that implies that the supernova explosion had to take place on the far side of the cluster. So if the observer is sitting here, the explosions, these two, happen on the other side of the cluster. So the part that is coming to us has to go into larger densities because the cluster is more dense in the center. So it has to go slower because it's moving into high-density gas. And away from us is moving faster because the density is lower. And that is what shifts the lines towards the red. Okay? We have made the numbers. We know the densities inside the cluster. We know the densities. We know the velocity because if you take half how you call it, half width at zero intensity. So this tells you the maximum velocity of the shock. So that maximum velocity allows you to know the temperature behind the gas. And therefore, if you assume that you exploded and you threw 10 to the 51 erg, then you finally can work out what is the size of the remnant that you are talking about. And it comes out to be of the order of 0.5 parsec. For the fastest one, you know, the one that is moving with 2,000 kilometers per second. And then when does it cool? Well, to cool down, you have to know the temperature and the cooling rate. The temperature is given by the velocity because temperature goes as the square of the velocity. And the cooling rate, I just showed it to you in the cooling curve, is about 10 to the minus 20. So the cooling takes place in a few hundred years. So once the remnant cools, then it's target of the ultraviolet photons, and that's why you see it when you take the spectra with your X-shooter. Okay? Now finally, I'm going to go to the other component because there's also this, the narrow component. The narrow component where you measure the metallicity of the galaxy, which is around 1/10 of the solar metallicity, where you know that the galaxy is centered at the position where it should, then that is tricky also because it's telling you that the strong wind that we have been using during all the talk has not interacted with the interstellar medium. And how come? That's impossible. And so what we have done is we went and measure the properties of this bubble or super bubble, as you like to call it, and we want to know what's the radius and what is the velocity. We went to the paper that first derived this, McLaughlin and McRae, and taking all the data of PHL 293b, like luminosity, the age of the cluster, the average density in the medium, we know that the supershell must be at 176 parsecs. That's well inside the galaxy. That has a radius of 400. Okay, so we are talking about something that is inside the galaxy. And the velocity is about 20 kilometers per second from this equation. Okay, from this equation, 20 kilometers per second is very close. It's almost the sound speed in the photoionized gas. The sound speed, because Instituto company came and measured the temperature, and it's about 16,000 Kelvin. That's almost, sound speed is there for almost 20 kilometers per second. So the shell is there, but right now it's being destroyed by the random motions of the interstellar medium. Okay? And therefore it's spectroscopically undetectable. You cannot resolve the shell because it's moving just in the same, with the same speed as the medium itself. Okay? Conclusions. So here we have the figure on the right is PHL 293b. These scales are totally distorted because I wanted to show you the events taking place inside the cluster, like the two supernova. This is the radius R5, where the temperature reaches 10 to the 5. This is the radius R4, where the temperature reaches 10 to the 4. This is the leading shock. This is a reverse shock that has caused a shell that has now a very low velocity. And outside you have this, I went back, you have this photoionized gas that composes the whole galaxy. I'm sorry, I somehow jumped. So I think now we know that the blue shifted absorption of stellar continuum is caused by the recombining wind between R5 and R4. There is an excellent agreement between the calculated and the measured column densities of ionized and neutral hydrogen. The red-shifted gold lines are caused by two supernova remnants caused by two recent explosions on the far side of the galaxy because they are red-shifted. And the narrow component must have a supershell, but it's moving very slowly. And that's why we cannot resolve it right now. There's another little thing that I want to mention just before I finish this thing. And that is the incredible thing that there are thousands of H2 galaxies. And the only one in which we know that there is this incredible absorption and the broad lines and the narrow emission. The only one is PHL 293b. Now, this probably is due to the fact that we have never, or probably never, I hope to motivate some of the people here, have looked for this absorption feature. It's incredibly small, incredibly small. And so to have it in paper, you need very high signal to noise and high dispersion. So I'm going to show it to you again while I ask for some, I reply to your questions. I'm doing again something wrong. It should, yeah. I did something terribly wrong, man. I'm sorry. It's only the river now. Thank you very much. Thank you.
Okay, thank you so much, Professor Tenorio, for this interesting talk. So, if there is any question.
César, please. Sergio, ¿me pones de vuelta en la pantalla? No sé cómo hacer.
Thank you very much, Guillermo, for this very interesting talk and work. Probably the galaxy is too weak, but is there any data in X-rays about the...
Yes, yes.
And
Actually,
how is-
Roberto also mentioned it in his paper, and we also have a beautiful agreement on X-ray data. I didn't put it in the talk, but I can give you the papers today. Certainly, yes, the X-ray is in excellent agreement also.
Is there any inference about the temperature or something like that to compare with the model?
This temperature comes out to be around, the X-rays are soft X-rays, okay? 2 to 6 kV. And I'm not to lie to you, I don't remember the number. I better show you the paper later.
Okay. And I am seeing now the spectrum. There is no evidence of a broad component in forbidden lines, no? In oxygen-3, for example. No, any...
I think one of the oxygen lines shows it. I think it's in around 4,000 and something. Just let me have a quick look.
The 5007?
5007 is not there. It's not there. So are the hydrogen lines that are showing these absorptions.
But the broad component is not observed.
It doesn't show in
In forbidden lines. Okay, thank you.
Very nice data and interpretation. What about high-resolution observations? Is there any Hubble imaging data?
No, I know. I really don't. I don't know. Probably. I will do.
So what resolution would you need to resolve those outflows?
Help me. I do a bit of hydrodynamics, but not much about telescopes.
What's
the resolution of X-shooter? I really don't know that number.
X-shooter is still limited, so...
Half a sec. Okay.
Yeah, both. I mean...
5,000. Mm-hmm.
Mm-hmm.
Well, that's the best image as far as I understand.
Yeah. Thanks.
So, if...
Now, what is the mass of the galaxy compared with the mass of the superstellar cluster?
Yeah, comparable. Around 10 to the 5 solar mass.
Both?
Yeah. Yes, the mass of the cluster is a few times 10 to the 5 solar masses. And in the narrow component, you have 1.2 times 10 to the 5. You can put on top these 3 times 10 to the minus 2 solar masses, but the masses are similar.
So basically it's a just born galaxy, because all the mass of the galaxy is that what, this is what I understood what you were saying. That the mass of the galaxy, the whole thing, is similar to the mass of the superstellar cluster.
That's what.
So it's a newborn galaxy.
Yes. Well, has had little star formation before, probably. And yes, that's what it is.
Let me make a comment about the need to look for these features in galaxies similar to this one. We have this library of like 10 or something like that, galaxies which are metal poor as this one, with high resolution, with high signal to noise ratio. So I'm going to look for these little absorptions just in case.
Okay, let me then tell you that if our cluster wheel results are correct, the speeds, the shift, the blue shift that you are going to see could go from 800 up to 2,000 kilometers per second. Okay? Depends on the age of the cluster. Sometimes it goes faster, the wind, sometimes it goes slower. But, so don't just look at 800 kilometers per second. There's a range of values you can look for the absorption, okay? Up to 2,000 kilometers per second.
It's about, I didn't get why you just get a blue shifted component, absorption component, rather than a blue shifted and a red shifted. Because the whole thing is actually...
You are the cluster, and you are throwing photons at the layer where the gas is recombining, and the observer is over there. Okay?
Yeah, but there are also the same layer is in the back.
If you were sitting there where Cesar is, yes.
So the
Cesar
photons that are produced there never reach you. That's what...
The photons from the continuum that were thrown to the observer are the ones that are absorbed. So the ones that are thrown away from Earth are going to be over there, you know, but that you can see.
I think it is very nice that you show so clearly the feature that could be expected for a configuration of the one that you have explained. That's very nice. Could you comment about the neutral and ionized gas that you say that it is very similar to the one that is measured? I mean, the fact that it is so similar could imply that before forming the superstellar cluster, you use all the hydrogen that you have, more or less. And the one you measure now is being produced by the cluster outcome. So it would be that, am I right?
No, I think most of the gas,
Yes.
most of the gas is sitting outside the supposed supershell. So in the drawings I have made, it's a pity we don't have a blackboard in this room. But if you allow me just for a second, now I don't have my arrow. I cannot see anything. Just allow me to reach one of my... No, I think there is a central cluster that is interacting with the medium that has produced a supershell. We have measured the size of the supershell. It's smaller than the size of the galaxy. And all the galaxy is photoionized by the cluster. Okay? Thank you. Thank you. Thank you. So the scales are totally totally wrong. So the cluster is 2 parsecs inside. Well, I have put it all the way up to where you see the stars. And the galaxy is 400 parsecs. Okay?
Yeah, but I wonder, could you please go to the transparency in which you derive the amount of neutral hydrogen, where you say that this is, which is about 10 to the 19, and the measured one is 10 to the 20. Go ahead, please.
Where I derive?
Yes. Well, here, all right.
This one.
So these resultant column densities that you derive
Yes.
come from the wind of the cluster.
It's the wind, and it's only the region which is recombining.
Okay. So, I mean, you have a wind producer, which is the cluster, which recombines, cool down, everything you have explained to us. And out of that, you get the density, the number of, the gas in ionized gas and the neutral gas.
That's right.
But the machine is the cluster, right? Okay, so what I'm saying is that it implies that most neutral hydrogen that you are measuring, that is measured, is being produced by the cluster outcome.
No. This. Oh, I see what you're saying. This is matter that was injected by the massive stars, and it's streaming as a wind, as our river. Okay. Okay. In that sense, yes, it's matter that comes from the stars. Yes.
So
Right.
that implies that this cluster was formed from a previous cloud, H1 cloud. So it would imply that, roughly speaking, all this cloud was consumed to form the cluster, and this is now resupplied by the cluster. So that would imply that the cluster was formed using much of the hydrogen that was available to form a cluster.
Okay, so remember, Professor Tenorio-Tagle will be here till April, so in case you want to interact more with him, and let's thank again.
You will be welcome. Thank you. Thank you very much. No se puede acostumbrar a esto, ¿eh?